Hi everyone. Today we are going to see how we can optimize routers by reducing latency, response time and eradicating buffer bloating issue. Well, in today's time, it is 2021. Uh, Buffer bloat is no more that much big issue because we are having the resources in plenty. Resources are not scarce. They are actually we are having no hardware limitations, but we actually have to optimize it in terms of time, latency, response time, latency and all. So how we can do that, we will be looking that in this video, and we will not be looking at the coding part, but I will be giving you the outputs and telling you what I actually did. Now this is the router, these are the routers, they are connected, they are sending the packets, each and every single client associated to them. And if I am having thousand of them, then it will be really important for me to schedule this router. Now, before any detail, let us just look at the buffer bloating issue and some overview of what we are going to do. Then we will do it in our Linux. Now, what we are having is this picture showing the round robin, these four queues. We can call them four routers from four different routers. These are the queues, packet queues. So this is my router having the queues from different other routers, four routers basically here in this scenario, and it is having some fixed memory. And if the requests at the same time, if we are having this many, at one instant, and if it is the size over there, these are the bit size, is exceeding the buffer capacity, then it will be buffer bloating issue, or over like buffer will be overloaded. We will not be able to hold that in this basket. Simple. Here we have already seen we are going to look into latency reduction and response time reduction and reduction in buffer bloating, and we are going to use FCFS, round robin and CFS. CFS is basically based on FCFS and it is called as completely fair process scheduling. And we should just look into these two and try to prove that a round robin is the winner in terms of buffer bloating. And it will be really hard for us to implement it in one program for round robin. So for response time and latency issues, we actually have to build a real time scenario to analyze it. So we will be doing it in single program buffer bloating and all, and then we will moving into this aspect of it and this perspective, and we will be looking and analyzing it that way. Let us go and look into it. I have already compiled it and run it just to save time of this video. I will be making other videos with explanation of the code. Let us go and look into it with overview. What we are having is number of packets for Q1 is 4. Number of packets, like we are having 4 queues as you can already see. So I have made this on the basis of this as generalized one. So it is going to use two things. Strict priority based on FCFS. Okay, FCFS and strict priority. And another one is round robin, as we have seen already that we are going to analyze using these two of the buffer bloat issue. And this is the Q3, Q4, and this is the number of bits in Q. Then we are having these, the maximum buffer capacity. These are the priority numbers. This is the like what I have over there buffer at this. Now priority number 2 for this is what I have, and for priority number 3 this is what I have. Now buffer capacity is overloaded. It's overloaded like that. In this also it is no buffer, then it is no buffer bloat. Now it is overloaded, so there is no buffer bloating, only one case over there, but here we have split it into 5 rounds. So basically we can see 75% is the efficiency in FCFS and 80% is basically the efficiency in round robin. This is basically hard coded and we are assuming we are putting it like this, so it's not a big deal. I actually didn't want to focus on this buffer bloat issue. Optimization in today's world is time. Let us just finish it off, and we have already finished it off. Let us go and try to look into it, what we are going to do in terms of around like response time and latency. We are going to make some router, the sending router. This is my target router. I will be analyzing the response time, basically the overall time for my stuff to happen and for each packet. Now let us go and look into the scenario that we will be building, but I think it will make you feel bored, and already you might be bored. Let me show one scenario. I am actually having FCF. If I just get branch, you can see we are having four approaches basically: FCFS, threads. We will be discussing that later on. They will be using CFS algorithm behind the scenes, and this is like thread pools. Then after that, thread pools optimize the best one. So we are already on the branch FCFS, so we can go and open some terminals. Okay, so we are having these two terminals, and I think I have already compiled it. I do not need to do anything, and I can do this. Boom. Can you notice something? These are the times I'm sending 50 packets from 50 different routers. So one router, for simplicity, basically one router will send only one packet. This is the time it took. Time user means basically that overall time the system has taken, because hardware is having, operating system is based on kernel. Over the kernel, this is the operating system. So overall, this is the time it has taken, and this is the time actually it took in the kernel. So this is what we have, and what we are going to do in this, like what is actually happening behind the scenes. Let me brief you over that right now. I'm having this multiple bash script. It will be generating 550 routers. This is the 50 routers RB Ruby file, basically Ruby script. Now in bash, I'm just calling this Ruby script with this modulo 5 plus 1, basically 1 to 5. And in this Ruby script, I'm actually taking that argument over there, argv0, and you can see I'm writing a destination. This is just to simulate the acknowledgement, just to tell the router, hey router, send me the packet, like that. For that simply I have just put some files, dump files, C program files, just basically anything that can be any packet. 5 files, 1.c, 2.c through 5.c, and it will be, each router will ask for one of the file, basically packet. Just to simulate it, I have considered file. You can think it anyway. So this is the fourth file, the fourth packet. I just stored the packets just to simulate it, because I have no real routers to implement it and to test it, but it will definitely work. So you can see in some of the scenarios the time is really going up. Okay, and this is really high time that it is taking over there. And let us go to the target router that we're going to do. So target router is basically make a socket connection. As you can see, handle connection FCFS, first come first serve. And this handle connection will, what it will do, it will handle the connection. It will check for the file. Just don't worry, I'm just not going to explain the code. I will make other videos for explanation. I'm just going to tell what we're going to do in this video. If you're interested, you can watch. And this is the file fp, and I'm opening it. If no open, it can't open, it will print the error and all, and we are closing the connection. So this is like connections, a router, another router talking. If it is not talking, then no issue, close it. Now let us go and simply or we can create new window of it, and in the new window I can tell you what is happening. This is my router, these are my sending routers. .1.c, 2.c, 3.c, dun 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 dun, 5.c, 1.c. Okay, so this is 5. Anyway, so these are the routers, sending routers, these are the receivers. So this is the my target router, and I'm storing the time, the clock I can show. This is the clock. I'm storing the time, overall time and packet wise time. So in FCFS we have seen that it is taking almost 2.51 seconds. Let us go using threads. Okay, so we are here in threads. In threads, basically what I'm going to do, each and every single router out there, each and every of the router will be assigned to a thread, and that thread will execute and it will come back just like that. It will be happening. So this is a thread function. In the main function, basically I have done that of network programming thing, and then we go, I'm just looking at the aspect of operating system in this video only, and we are having this p client, p thread create, null, handle connection. So handle connection is the function that this thread requires. For each and every single connection I'm creating a thread. And this is the p client. Okay, so you can see in the handle connection I'm not doing anything or there. I'm just simply doing the same thing. It is actually the same, except it is having some void pointer and just casting it back to an integer client socket and freeing up the void pointer that I got from there. So nothing special, only one thing, each and every single thread, if I'm having 50 requests, it means 50 threads, and you will see that it will be a disaster to have 50 threads, because practically it will be a problem rather than being a benefit. I think it will work because we are in this, we have checked out 2 threads, so this is already compiled, everything is compiled. Come on. This is waiting for the connections. Let us go time multiple bash. So you can see, just don't look at it is point something, difference is big. If you look at the previous one, the difference is higher. Why it took higher time? Because we are having 50 threads. We don't need 50 threads. What is happening? This is the router. In this router, basically this is my queue. This is my queue, packet queues or routers basically. First router, second router, third router, fourth router, n number of routers. And from this queue, I'm having these threads, the thread pool. Basically, thread pool we'll be using later on. So whatever it is, the number of queues, if it is 100 queues, 1000 queues, 1000 number of packets in this queue, sorry, 1000 number of routers connected, then it will have one thread for each one of them, and it will be really painful for the context switching. Context switching also takes some time. The CFS will be working, these are the threads over there, equal to the number of threads over number of routers over there, and they will be processed using CFS of my Kali Linux that I'm using operating system. So they are processed using CFS, but the context switching that it is taking help of is itself taking a lot of time. So despite in spite of having the benefit, we are actually going to get into some loss, and we have already seen it. So let's go and look at our new approach, and which is really amazing. These are the thread pools. Can you notice 2 more files? This is the FIFO queue, because I actually, whatever the connection request comes, whatever router I am having 50 routers suppose, so they will be instantly put into the queue. one by one. It it's real time, everything is real time because we are recording time for each and every single packet. The time is being recorded. Now FIFO queue is simply handling the queue, first in first out basis queue. Each and every single router connected will be put into the queue. Now what I'm going to do in this is actually we have to obviously do mutual exclusion and all. We have used mutex here. We have used mutex here also so that we can do mutual exclusion. In previous one problem was also the time and another problem was mutual exclusion. So in mutual exclusion we can see, okay, mutex. When we enqueue, into it, actually two of the packets can be enqueued at single place in the list that I am having FIFO queue. In the FIFO queue, two packets. So this is something that is not thread safe. I have to apply a mutex lock into it. And similarly, in the thread function that I'm going to call for each and every single thread, I'll be telling the thread pool thing just in a second. And while I'm also dequeuing and queuing, I am just putting them in between the mutex lock. So this is what I wanted to clarify. Let's come to the thread pool. In the previous video, in the previous scenario, basically, the threads, simple threads, we are having 50 packets, suppose, then we are having 50 number of threads. And that is really painful for the processor. And instead of reducing the latency, it will increase it. So I'm limiting the thread pools. It can have at most 5 threads at one time, and they will continuously be running in this case. And basically, let me tell you also what it is. This is server backlog queue size, the number of, like, the limit buffer bloat, the limit of my queue, the limit of the FIFO queue. This is the number of connections I can have at one instant, not the number of connections, basically number of requests from 100 routers simultaneously. This is it. So this is a buffer bloating. I can put 1000 also, I can put anything, that's up to me. So here thread pools, you can see in the main function I am creating each thread, like we are having 10 threads, so we are creating 10 threads and passing this thread function. What thread function will do, let's go and check it out. While true means always it will do p client q dq, and it will handle the connection to this, and handle connection will handle the thing like this. So handle connection is simply that we have used in previous one, which is the thread function. So let us go and just look into it, how much time it consumes and how it is working, how well it is working. Let us go. Okay, I have to compile it. No issue. Let's compile it. GCC. Okay, it's already there. Target router.c, FIFO.c, I have to also include that, and output will be router, and LP thread I'm including out there. Process threads. Okay, let's go and run it now. It's running. Let us go and run it also. You will see. Can you see reduction? It was 2.56 something for the FCFS and 2.6 something for this, and it is really less for this one, which is 2.54. So it's working. But let me tell, my laptop is about to blast. Trust me. Let me show you. If I go top, and you will see, boom, it is consuming lot of CPU. It is at the top. I mean, I have very big machine and it is at the top. What is happening? Let me close it before my laptop blasts. Come on, closed. After I have sent all the packets, because I have 10 threads in my thread pool. Now you can see it is gone. If I just check it again, top, you can see it is gone. So you can see that it is really being very much problematic for the machine. If you have low grade machine, low grade router, then it will be a problem, and your router may catch fire, it may blast, or something nasty can happen. Basically it will be really efficient because all the threads in your thread pool, which is the 10 number of threads, will be continuously looking for the packet. Continuously they will be searching for the packet. However, that may be a problem if you need to optimize it. Now we can also optimize it. We can make the thread to sleep if no packet is there. Are you getting? When I run the top for the first time, I had done all my processing. I have sent 50 packets, I mean 50 routers, 50 packets, and I have recorded the time. Everything was over. There was no request, no packet that was to be sent by the router, this target router. Even then, it was at the top and it was running continuously badly. So, for that, we may want it to sleep when there is no connection over there. Let us go into the next case. Git checkout. All right. So we are in this optimized version. In this optimized, we are actually doing one thing, as you can see. If I go into the thread function, you will see I have changed the code a little bit. I will be telling you that. In the QDQ, I'm using this, and can you see this condition variable wait and all? So this condition variable I'm using within this. So mutex condition variable is special type of condition variable that is there in this Linux by default, Unix operating system. It will work with the mutex and help me to actually do conditional variable thing. That logic we can implement working with the mutex. So just everything is same as previous one. What we are doing, like we are having 10 threads, thread pools. We are having p thread condition signal after the enqueue. It means if any packet is there that is pending, and any thread is sleeping and packet comes and all the threads are sleeping, it will try to lift them up. In a scenario, I am done with this routing. I have sent all the packets, received time, everything is closed. Now, since all threads are closed, it can't do anything. I have to lift them up. So whenever new connection comes, it tries to lift one of the threads. If all of them are sleeping, no problem. So this will just for the safe side, and basically we have to do it this way only when we receive a packet, and mutex and look everything same. Now this is the ptex thread mutex lock we are applying as done in the previous one. Now in this we are going to check if p client after dq will give something to the p client, which is actually the next packet, next connection, next router, whatever you call it. And if it is null, it means empty. Then I will make that thread to wait. I will put that condition variable and mutex. So this is the condition variable defined over there. Okay. So I will just lock it and I will try to dequeue it again. Okay. And after that I will unlock it and everything will happen the same way. Let us go and try to look into it. There is no need to sleep it up. It will take time, obviously. So here let us go, and I have already done it, and let us try to check it out. How much time it takes. Remember from previous one, boom, it is taking too much time. Why? Because it after like it if it doesn't have anything over there, it will make the thread to sleep. And mutual exclusion and all, they are also taking some time. So unnecessarily there is no need to do it. But if you have a slow system and you have a hardware, or you are something like you don't want workload, you want your router to last longer, which is not the case, But anyway, if you have weak system and you don't want too much overload on it, you can configure it this way. Now if we go and look in the top, you can see, I think this is from the previous one only. Let me compile it again. It won't happen this way. I have to compile it again. GCC. Let me cross check if I am in optimized ones or not. Yeah, I'm in optimized ones. So let me compile it again. Let me run it. Let me send the packets again. Obviously it is less, it is much less, 2.53 seconds, and it was 2.65 seconds. So it is much less. And also one more thing is over there, we can look into it. The top command, and you will observe it is not there on the top. Hence we can say like it is really efficient. The optimized routers is really efficient. That's it for this video. And if you really want me to explain how it is happening, then like the coding part, what is implemented, how it is implemented, then I will just be happy to make a video on that. So what we have observed over there is we have done 4 approaches in that scenario, which is for the response time and latency basically. So we have done plain FCFS, we have done simple dump threads, then we have used thread pools, then we have optimized the thread pools, and this is O for optimization. So this is what we have done. You can have them, they're running really good. If you have weak hardware and you want them to sleep and take some rest, if no packet is over there, then you can use optimized thread pools. So both of them are good and amazing. And this time you can see this time it is taking like 2 point where is the time, yeah, it took 2.53 seconds. It should be more, but because this is not the real router, that's why. So you can see this even taking less time now, 2.62 like, yeah. So basically it depends on how much load is there in my Linux, because CFS is being used by my operating system. I have not implemented that individually, that's why that issue was there. But we have observed like what is there ideally in ideal condition, what will be there in ideal condition. This will be the most efficient when there will be load. This will be good, but least not lesser as compared to that. This will be disaster. And this is simply dumb thing, but it works. But buffer bloating will be a problem with this. So in my consideration, if you really have very powerful hardware built in for just a router and amazing hardware, just go for it, we can implement it. And if we have some like pretty good, but basically it is a problem, uh, it can't take the workload that much, so we can have this optimized thread pools. And obviously if you don't have multi-threaded multi-core routers, I mean you don't have any you know you don't have any multi-cores obviously, then there is no need for you to have these all things, because multi-cores are actually not able to work well with threads. Obviously one thread will be executed, so you can't execute anything in parallel, so that will be an issue in multi-core processors, the processors that are not multi-core basically. So that's it for this video. Thank you for watching, and I apologize, it is really long video and I messed up a lot, but I conveyed, I tried my best. And if you have any like queries, you can ask me, and I'll be making a video on how to implement it also if required by any one of you. Thank you.